All right, welcome to this webinar. I hope you can all hear us. Brian and I, we are from Data Analytics in DHI, and today we're going to tell you about fast reduced order models for efficient coastal ocean simulations, how you can build surrogates based on your Mike model inputs and outputs. And so the title is saying coastal ocean simulations, but it could also be results from other Mike models. But first, let's start with a presentation of who we are. So my name is Jesper Marigo. I have a background with a PhD in applied mathematics from the Technical University of Denmark. I've been in DHI for 15 years in various positions, working on operational forecasting, wave modeling. I've also been leading the development of Mike 3 Wave FM. I've been responsible for implementing data assimilation in our marine Mike models. Or in more recent years, I've also been working a lot with machine learning and hybrid modeling, both on research and commercial projects. And since last year, I've been the head of the data model integration team.
Yeah, hello. My name is Freja Petersen, and I'm a somewhat new member of Jesper's team. We've been working since March as a machine learning scientist, and where we'll soon be studying a PhD position, an industrial PhD between DHI and the Technical University of Denmark. And before that, I have a background in mathematical modeling from DTU.
Yes, all right. So briefly on the agenda for today, we will introduce the sort of overall area within we are working with, the test cases considered in this work, methodology, and show some of the results that we have seen, and then finally close off with some discussion and outlook. And we will very much like to engage with you. So please feel free to write questions in the chat as we go along. We will try our best to take them as we go along, if we can, and otherwise we will have time in the end for more questions. All right, our starting point is the flexible mesh coastal ocean models, Mike 21 and Mike 3, which are using a finite volume method to solve different types of simplification of the Navier-Stokes equations to solve for say, the flow of water in a coastal ocean area. These type of methods or models are quite important for engineering applications and used for both design and operations of, say, for example, offshore infrastructure or many things at sea. But as you are probably aware, they can also be quite computational heavy, because in order to describe all the different processes at sea, we need quite a lot of resolution. So sometimes the degrees of freedom of these models could be around 100,000 or even 1 million or even more. So they can be quite computational heavy. The topic of the talk today is surrogate models, and the starting point here is some high-fidelity geophysical dynamical system like the one we saw on the previous slide. So it could be Mike 20, Mike 21, or Mike 3, or another Mike model, or another type of geophysical model. And when we talk about a surrogate, then it's an approximate model which emulates the original model, but is much faster. Often also hear the word emulator for the same thing, and that's used synonymous. And surrogates can be constructed in many ways. It can be derived from sort of a conceptual physics, or it can be constructed in many different ways. And what we are considering today is this talk is data-driven reduced order models, which are trained on inputs and outputs of the original model. I will of course explain that a lot more in a minute, but let's first get to know you a little bit. So we have prepared just 2 small questions for you.
I will try and share.
I think you just click start
Here. All right, so there should be a poll that's showing up on your screen now.
Two questions. So the first one is how much experience you have with mic modeling, and the next one is on experience with machine learning.
That's also because I guess we're maybe collecting people from different backgrounds here, some who have worked with mic and not a lot with machine learning models, and vice versa, probably. Maybe some of you have a bit of experience with both.
Yeah, so we can see that the results are showing that almost all of you have experience with mic modeling, as we would expect, joining this webinar, the entire webinar. We also see that most of you have some hands-on experience with mic modeling, and then we see that around a little more than 1/3 of you have no experience with machine learning, and then most of you that have some experience. Thanks for the answers. So let's have a look at what you could actually use such a surrogate model for in the case that you had one. So, and that's also the motivation for doing this work that we're doing. So if you had a model which is 1,000 times faster than the original model, then new opportunities could open for you, right? So you would be able to do really long simulations. For example, long climate scenarios, maybe say 5 or 8 different climate scenarios of 100 years. It could also be that you want to do ensemble simulations. So many of the inputs for our mic models today are with ensemble. So our ensemble weather forecast models, or for example, can be used to generate ensemble mic simulations also. But if your model is really heavy, then it's not so easy to work with. But if you have a really fast surrogate model, then you could do probabilistic forecasting. Maybe you could even do data assimilation with the ensemble kernel. Yes. So our goal with this work have been to build a surrogate of a flexible mesh coastal ocean model, which is 1,000 times faster while retaining 90% of accuracy. So that's sort of the overall goal here. And we have been studying 3 different cases. The first one we have been looking in more detail, and that's also today. We will also see much more detail about the first one, but we have also done 2 other ones. So the first one is the sound between Denmark and Sweden in relatively coarse model here with around 18,000 elements. The dynamics is governed mostly by the search component, but also with a minor title component. And then this model is quite strongly driven by the boundary conditions. So we have 2 open boundary conditions, one in the top of the domain and one in the bottom of the domain.
I think you were not seeing the screen.
They will. Thanks for raising that. Should be seeing this screen now.
Yeah, I also see it here. I don't know when we lost it, but
probably around the all, I would guess. But yeah. So, but I think I mentioned this. So I think I sort of read it aloud, right? So we are considering this model domain of the sound between Denmark and Sweden called Ørsel, strongly driven by boundary conditions. So we have compared also to a few measurement stations in this domain. There's two here, one in Dråben and one in Klakshavn. And as you can see, the model is performing okay. It's not super good, but that doesn't really matter so much for the purposes of this presentation. The root mean square error compared to measurements is around 4.5 centimeters for these two stations when you compare to the original model. Yeah, and the scatter plot looks like this. All right, so we have done a 1-year Mike simulation, Mike 21 simulation for this domain, and taking sort of a snapshot for every 30 minutes. So that leaves us with 7,520 records of the state. The state consists of the surface elevation and then the two components of the velocity, current velocity. We also save the forcings used here. So that's the boundary conditions and the wind and air pressure. And we split the data in these two parts. So 8 months of training the surrogate model and then 4 months in the end of the year to evaluate the performance in our test period. The two other cases are a bay in Canada, Conception Bay, and then the Adriatic Sea, which features different type of dynamics compared to the original model. So in that way, we have tried to evaluate the performance of the model on different types of use cases. We call the framework that we have built the flexible mesh reduced order model. It works in this way. Our starting point, as I mentioned at the beginning, is a physics-based model, a Mike model, which essentially takes the state of one time step plus some external forcing. So in our case, it would be the open boundary conditions and the meteorologically conditions on top of the water and maps them onto the next time step. So that's what you see here. The state, surface elevation, and two components of the currents and the forcings. We integrate and get the next time step. So that's how all the Mike models and similar models are working. And yeah, since we know that the solutions and also the input here is relatively smooth, we want to do a low order representation of all these states. So our state here has a dimension around, say, 50,000 because it's for all the mesh elements and then with the three variables that we have. And then we have a lot of snapshots during the year for that. And the same we have with the forcings, so winds, air pressure, and open boundary conditions. And then we believe that we can do a mapping onto a small space. So just taking sort of the modal representation, the sort of soft or the most important part of the signal in this case. So maybe we will reduce from 50,000 down to 50 or something like that. And the same can be done for the forcings. And how we do that, we will come back to in a minute. But assuming that we have such a mapping, then we can consider what goes into the Mike model and what goes out to the Mike model. And then you can see down in this latent space, we now have the latent state, but we also have the latent forcings, both as input and output. So down here in this small low-dimensional space, we can build a regression model. So we can train a machine learning model to do this mapping from previous time step with the forcings onto the next time step. And then we can map back again onto the physical space. So that's sort of the idea of the reduced order model here. We map down to the latent space, find the next time step and map back. But since it's just any old regression model we can use here, we can also add in previous time steps. We could also add some sort of external information, say day of the year, whatever we would find that could improve our regression machine learning model down here. But Brian, maybe you can take us through some of the details.
Just switch computers here quickly. Yes, so as Jesper introduced, this framework we built is consisting of these two steps. So we have a dimensionality reduction and we have a regression model in a latent space. And in our implementation and in the results I'm going to show in a minute, we use a principal component analysis for the dimensionality reduction. And then we test 3 different approaches for the regression model. And now before digging into the details, I'll just remind you that the reason why we're doing this is that we want a really, really fast model, but there's also some other things that are important. So we especially want the model to be simple and interpretable, and that's also why we use the principal component analysis, and I'm going to show you why. But this is, the simplicity is also so it could, for example, be more easily implemented in an operational context. It wouldn't require a lot of maintenance and interpretability, so we can understand if the model is doing something that seems reasonable. So I'm going to go through these 2 steps. So we're starting with the principal component analysis, where I'm not sure if all of you know this. I saw some had no experience with machine learning. And I would say this is kind of a machine learning technique, at least where we're learning something from the data. But what the principal component analysis does is to find an optimal subspace for representing your high-dimensional data. So in this toy example here, I have some 2-dimensional data in x1 dimension, x2 dimension. In this case, it's a classification task, but it doesn't really matter. But we have some data here, and we want to find a projection or a directional vector to project the data on, to have it represented in a 1D space instead of 2D. And then there's a bad way to do that and a good way to do that. The first here is not really a good way because we can't really, the data is not well separated. Whereas in this last case, it's the optimal direction for separating the data. So the principal component analysis essentially just finds these directional vectors. So if we have something very high dimensional, we can find maybe 10 vectors to span our subspace. So that's the idea. And in our specific case, for the Øresund case, we have a lot of mesh elements. So in this case, we have 18,000, almost 18,000 elements. And if we just consider those, like each of those like 1 dimension, we can say we have an 18,000 dimensional space to represent our data. And so what I want to do if I have 1 data point in time, then I want to project that onto just a 1-dimensional value. So the way I'm going to do that is to find some coefficients from these directional vectors, my A coefficients, B coefficients, so that's the 2 first directional vectors, and project it onto a single value. And the cool thing about this, so it's a linear projection, and the cool thing about it is that we can then go and look at these coefficients and because there's a coefficient for each of the original dimensions, so for each mesh point. So I can go and actually plot the coefficients or plot the magnitudes or the values of the coefficients on this spatial representation. So this is the first directional vector. So if I want to reduce from 18,000 to just 1D, I would use these coefficients. And we can see that this first principal component is considering a difference between the north of the domain to the south of the domain. And the next one is separating the south of the domain from the north of the domain, and so on. And in the fourth one, we can see there's a separation between east and west. So what we can use this for is to do a reality check or a sanity check and say, with what we know about this domain and this data, does it make sense that it's very important to separate north and south? And like Jesper said earlier, this case is very driven by the boundaries. So, and we have a boundary in north and one in south. So it does make sense. So I use this for saying like, my latent space actually, it is sensible, it makes sense. But the next task is then to decide how many principal components to use for spanning my subspace or my latent space. And for that, I can do some different analysis. So this is the explained variance ratio for each or a number of components. So the more components, the more of the variance I explain of the data. And this plot shows the reconstruction error. So if I have my data and I project it to the latent space and just project it directly back without doing anything with regression models, then this is my error just from the projection. And of course, I want this error to be as small as possible because my surrogate will, in the end, never be better than this reconstruction error. There's also, we can also plot like spatially what does the reconstruction error look like, and we can see that along the boundaries, it's a bit more difficult to represent the data with a linear projection. But the more principal components we include, the more we can actually represent. So the lower error, this is the error I'm plotting here. Yeah. So in my case, in our case, I use these rules, North's rule and Kaiser's rule, and I'm not going into details, but these are just guidelines for choosing the number of components. And I end up with these number of components for the 3 state variables and for the 3 test cases. Yeah, and I also have the reconstruction errors. I'm not going to spend a lot of time on this slide, but in case you were curious, you can see them here. We can always return to it. And similarly, I have also for the forcing data, because as Jesper said, we're projecting both the state variables and our forcing data to a latent space. Yeah. So this is the first step of the task. So for the first task, the dimensionality reduction. And then the next task is the regression model. We test 3 different regression models. So once we have projected to the latent space, then I test 3 different regression models. So there's a linear regression with simply just a linear mapping from one time step to the next. And I have a multi-layer perceptron, which is a neural network with a number of hidden units and hidden layers. And then these units are fully connected. So going from an input to an output, where the output is the next step. Then I also test a gated recurrent unit. Maybe some of you have heard of a recurrent neural network, or maybe an LSTM, long short-term memory network. The gated recurrent unit is just a type of recurrent neural network that's a bit more stable than the recurrent neural network. But it has a reset gate and an update gate, and it's essentially learning how much of the past data to remember to predict the next time step. That's the idea in a recurrent neural network. Yeah, and for each regression model, I have some hyperparameters to tune. So for the linear regression model and the MLP, I have the number of lags that Jesper also mentioned before. We can choose any number of past values to give us input. So that's a hyperparameter to tune. And for me, the MLP, there's also something like the number of hidden layers and units, things like the regularization factor also, which optimizer to use. There's a lot of decisions to make there. And for the gated recurrent unit, there also, we don't have to decide on the lags here because that's something that the network does itself. But then it has a lot of other parameters. And I can say just briefly, going from left to right on the slide means increasing the complexity, both in training time and hyperparameter tuning. So I prefer in terms of the simplicity to be more towards the left. Yeah, so we train these regression models on the training period of the first 8 months of the data, and we test on the last 4 months, and that's with an iterative forecast. So once we have trained the model, we do an iterative forecast and not just one-step predictions to evaluate the model. And we evaluate the model both by comparing to the high-fidelity model, in this case, the MIC model, so the simulation data that I use for training. But also, we do sort of a sanity check by comparing to observations. So sort of as seeing how much would this error matter in the real world. And I compare by using these metrics. So the root mean squared error is a good aggregated measure where you take into account both space and time. But the R squared is also sort of normalizing using or by the variance of the data. Yeah. So that's the task. That's the idea of the framework. Then I've tested this and I'm going to go through the results. So we'll see if it's a good model or not. So first, this plot shows the predictions of just a little snippet of the test period, just so it's actually possible to see something. And we have the 3 different regression models. There's also a baseline model, which is simply just predicting the mean value of the training period. So it's not that interesting, but hopefully the other models are better than that. And then I also plot the MIC model, so the training or the simulation data. And then the dots are observation points or observation data in this measurement station in Sweden. And yeah, so we see that in general, all models follow the data quite reasonably. It's a bit difficult to distinguish them from the models from each other, but something I do note here is that especially the MLP has some large fluctuations. And the reason for that is that it doesn't really generalize well outside of the training period, which I'm also going to show in a minute. Whereas the linear regression model, which is the dark blue one, and the gated recurrent unit are somewhat the same or look somewhat the same here. In this figure, we get a bit more information. I'm showing the root mean squared errors across the spatial components. So this point here, for example, is a point in time, and then I have the root mean squared error across space. So I'm showing box plots so as to see the spread of the error across time. And in general, if we look at the surface elevations, yeah, and this is the training period and this is the testing period. And if we look at the surface elevations, the models seem to perform somewhat equally well. But as soon as we go to the test period, so go outside of the training period, we see that the MLP doesn't really generalize well. Also, the gated recurrent unit is a bit worse too than the linear regression. So in this case, I would prefer the linear regression also for the performance. But if we look at the current velocity components, U and V component, we see that the MLP fits way better, and also the gated recurrent unit. And then in the test period, the gated recurrent unit also is a little bit better. Whereas the MLP is once again not generalizing very well. So from this, you might want to choose the gated recurrent unit if you want a high accuracy, but the gated recurrent unit is very, very heavy to train. So for the next slides, I'm going to show you results only with the linear regression model, because that's my preferred one in that sense. Okay. Yes, so here I just show again a time plot with only the linear regression model and the mic data. And this is just to show that qualitatively there's not a big difference in the surface elevations, whereas in the velocity components there are quite big visual differences. So same conclusion, it's not as good there. In these plots where we show the mic predictions versus the surrogate predictions, we see the same conclusion again, that for the surface elevations, the predictions of the surrogate are very close to the mic model predictions. So we're quite happy with that. Whereas for the velocity components, there are some clear nonlinear trends. So it's the linear regression model is simply not capturing the nonlinearity well enough. And this is something I guess is expected if we're just using a linear regression model. And then I should probably say at this point that we formulated the surrogate model framework in a very flexible way, such that if it's important to the use case to be able to represent very well the velocities, then we will probably just switch the linear regression for some other regression model. So it's quite flexible. But if I'm mostly concerned about the surface elevations, then I'll be very happy with the linear regression model. So that's a main point here too. As Jesper said, we also tested for the two other test cases, so the conception bay and the Adriatic Sea. And this is just to see if we could do well enough on some other use cases now that it seems to work quite well on the Øresund case. And we can see if we just look at the spatial root mean squared errors, that it's going quite well for these two cases too. There's slightly larger errors in the northernmost part here. Overall, it's quite well generalizing to these two cases. Then I promised also some numbers with the metrics, the root mean squared errors and the R squared. And once again, we see that across the three test cases, the performance is quite good for the surface elevation. Whereas for the velocity components, the performance for the two test cases, conception bay and Adriatic Sea, is not as good as for the Øresund case. So if we look at the R squared, for example, we're in 0.7, 0.6, and we want this to be very close to 1. So once again, it's the trade-off. If it's important for us with the current velocities, then we should probably choose a different regression model. This is sort of a discussion point with this method. And then if we compare to observations, so here I take the mic model results and compare to some observations. So this is surface elevation observations in some measurement stations. Then I show the root mean squared errors in this row. And for the surrogate model, I have the root mean squared error in this row. And in the last row, we have the increase in percent when using the surrogate instead of the mic model, or the increase in percent going from this to this row. And across the test cases, we're we're below 5%. So with the goal Jesper mentioned in the beginning of retaining 90% of the accuracy, I guess this could be one result that, okay, we only have a 5% increase in the error. So retaining 95%. So in that sense, the surrogate is also performing well. And visually, the comparison to observations, we have some QQ plots here with the mic model and the surrogate model. And I should mention here that there's a larger error for more extreme values, or larger error of both models. And that's also because the mic model hasn't been calibrated to perform especially well on these values here. So that's the reason for the error. But we see that when there is an error, there will also be an error with the surrogate. And so the main point here is that the surrogate will never be better than the training data. And that's, of course, something to remember. So the main point is also that we need the mic simulations to train the surrogate models. Yeah. Okay, and now a fun slide, because this is, of course, the reason why we're doing this. So with this quite simple setup with the PCA and a linear regression model, I have a speed up factor of 1,000, 950, a bit more than 1,000. So it's quite a lot. And that's like as I said, the main reason for doing this. And this is the speed up factor in the inference time, so during the forecasting period. But the training of the surrogate in this case, I would say, could be disregarded because it's a linear regression, so it takes a few seconds to train compared to the neural networks that required a bit more. Okay, so in summary, can we build a surrogate that has 1,000 times speed up and retains 90% of the accuracy? Yes, we had a speed up of around 1,000. And the accuracies were also quite well, or the errors were quite small when we're comparing to the hi-fi model, the mic model. But also that when we compare to measurements, there's only a small increase when we're using the surrogate instead of the mic model. A discussion. So I touched upon some of this. So I said that the linear regression that I showed results for has limited performance for currents. But as I said, it's a flexible framework. You can also use a different dimensionality reduction if you want, but and a different regression model, so you can sort of fit it to the use case you have. Then I want to touch upon this with like data-driven models. You're not guaranteed that they generalize both outside of your test or training data, but also to other test cases or outside of your spatial area. And that's because you don't really, you can't be sure that it learns the right thing. But then I wanted to put in the future work of first point that one way of approaching this challenge is by using the knowledge we have of the physics to include inside of the machine learning model. And this is a sort of an emerging field and something that's moving quite fast right now with physics-informed neural networks, for example, that can ensure that your model is like
abiding the laws of physics.
Yeah, abiding the laws of physics. Yeah. Also, I mentioned it a little bit that we need the mic data to train the surrogate model, and it could be expensive to generate this training data. So there's some future tasks in looking into how to optimize this generation of training data. But also, like, this is an interesting machine learning task when you're working with synthetic data. You can also do synthetic events and like make up events that could make your surrogate perform better. So this is an interesting task for the future. Then, of course, also using the surrogate approach for other mic models. I just presented now for some coastal ocean models. And then also mesh independent approaches. For example, there are things like neural operators, where, so that's like a piece from literature where you're training not a model to map from input to output, but that maps from functions to functions instead. And this means that it is mesh independent. And this is just an interesting take on surrogate models. That could be something that, then I have this, that I could look into in the PhD project. So maybe you'll see more of this in the future from us.
Yeah, and to round off, we also figured that it would be interesting for you to see what could you do. If you are interested in this, then you can learn more about by reading the paper that we have just submitted, and we will, you can get in touch if you wanna see that. And of course, we will also let you know on via LinkedIn when the paper is available. You can also implement this yourself. We have provided some details about how to do it, and if you need to do this in an operational setting, then say that it's doable. I have certainly shown that it is doable. So you can do that. Alternatively, you could also ask us in DHI to build that surrogate for you in an advisory project or as part of the digital solution. And maybe in the future, you would see some sort of option in the mic modeling system where you could build a surrogate directly from the mic interface. That we would like to see, but it's not. It's probably not next year, and not something which is planned. So with those perspectives, we would like to thank you for your attention and be happy to answer any question you may have. So yeah, thanks for listening, and feel free to raise your hand or write in the chat. I can see there's already the first question.
Can you read it?
I'll read it. So the question is the number of components the only factor affecting accuracy? Can you correlate the accuracy with the degree of reduced order?
But the number of components is not the only thing affecting the accuracy. I don't know when this question came in, but
like a few minutes ago.
Okay, but I think I also touched upon that the regression models affected quite a lot. So you can control or you can increase the accuracy to some extent by tuning the number of components, but as soon as the reconstruction error, maybe I should jump back to that slide. As soon as it is low enough, so I'm thinking of this slide, as soon as you have a reconstruction error that's below 0.1 centimeter, then it's mostly the regression model that's controlling the accuracy.
Yeah. So, but of course, it's a prerequisite that you can represent most of the variability of the original system in the latent space. But it's no guarantee by just having enough components that you can actually build a dynamical system, a model representation in the latent space. So, yeah, but good question. Mm-hmm. Yeah. Any other question? the presentation was super clear then. But feel free to reach out to us if you. Oh, there's one more here. If you only need the prediction at a limited number of locations rather than the entire model domain, then presumably this is easier. Would you still apply the same method?
You want to take it?
Yeah, maybe I can take that. Yeah, we actually also have worked with alternative methods. So the purpose of what we're doing in this project is to do a full drop-in replacement of a mic. If you're only interested in a few different positions, you can also go for simpler methods, and we are also doing some work on that. So we actually have a commercial offering now, I think. Maybe that's for the time mostly for wave models. It's called the MetOcean Simulator, where you do sampling to get some good training data, and then you train a more point-based time series model. So if that's what you offer after, then you can also go for a simpler model. Yeah, but good question. And you can say you could use more or less the same technique here, but skip some of the steps, because then you're already at a low dimension. All right. Oh, any plans of using the reduced order model for speeding up the simulation of the hi-fi model? Well, maybe you can. Carlos, maybe you could elaborate a little bit of what you mean by that, because it is. So currently, what you can do is that training a surrogate model here that would result in a reduced order model that you could then run sort of offline. And you could run many versions of this, or you could run them for a very long time, and that will be 1,000 times faster. But it will not directly affect the original model. So I'm a little bit unsure about the question. If you're using an iterative method for solving the hi-fi model, yeah, it's currently in the mic models, it's not using an iterative method, but I see the point. I guess maybe the closest along that route is, I mean, we are considering to use it together with the data assimilation with the ensemble Kalman filter. And there you would sort of need the model to access the surrogate of itself for doing the state error covariance prediction. But I see your point, and you're asking also if you could use the ROM as a better guess, for example, for the next time. But it's not exactly that how that model works. It works with a finite volume model. I mean, the original hi-fi model is implemented using a finite volume approach and using an explicit time step integration. Then another question is, can you remind me what the physics-based mic model you used to train the surrogate model? It's mic 21 HD. So
I'll just find the slides there.
Yeah. So it's yeah, the 2D version of the mic FM model. But as this framework is quite flexible, it could also be used for some of the process models on top of this. So for example, for sediment transport or ecological modeling or 3D modeling, but it could also be used for groundwater models, potentially also network-based models in urban drainage system or rivers and so on. Because essentially how we treat the data from the original model is just as a vector for each time step. So that's very flexible, and that's also why we call it FM1. Yeah. Let's close it here. So thanks a lot for attending this presentation. I'm quite sure that you will receive a mail with the slides and probably also a link to the recording of this webinar. So thanks again for attending, and see you some other time. Bye.
Bye.